Hello and welcome to Sean White's Solar and Energy Storage Podcast. In this podcast, what we're going to do is we're going to read my favorite wire sizing article called Code Compliant Conductor Sizing. And this article is from the 2011 version of SolarPro magazine, which you can get still at solarprofessional.com. So this is the April-May 2011 version from SolarPro magazine. So this article, it's super advanced. It's the most advanced thing I've ever put on a podcast. So what do you do when something's super advanced like this? You sleep on it under your pillow and let it play over and over again like 100 times, and then 100 more times, and then you'll memorize it. Another thing that you can do is just listen to this and let it get familiar with you, and then listen to it again another time, multiple listening to things extra times. And another thing that I did when I was first learning about the National Electrical Code is I just listened to stuff just so I could get the terminology down. But if you are already NABCEP certified or you're an electrician, you'll probably get a lot of this. But I also recommend studying up on this using my classes or my books where you can really sit down and figure out how to do wire sizing right, because you know what? Most people do not do wire sizing right, and this is how you're going to do it right, and you will be one of the few. Enjoy the show. To learn more about solar and energy storage, go to solarsean.com. Hey people, what we're going to do right now is we're going to read this SolarPro article, and you can find this SolarPro article at solarprofessional.com. SolarPro is sort of no longer in business, but you can download every edition that they've ever had. This is April-May 2011. That's 10 years ago. What I'm going to do as I read this article is I'm going to read it and then I'm going to make comments on the article. So let's get on with reading this article. It's called Code Compliant Conductor Sizing. And just a little bit of background on wire sizing, otherwise known as Code Compliant Conductor Sizing, is it is very confusing. Most people don't know how to do it. Most people that are NABCEP certified don't do it right. You're not going to really see this kind of detail on any NABCEP test, but it's a good thing to know how to do. So, on with reading. Conductor sizing is a critical step in PV system design. You must be sure to satisfy the NEC requirements for both the conductor's ability to carry current and the performance criteria for the power delivered. To properly size conductors for the NEC, you must determine the correct current to use, the conditions of use, and the required overcurrent protection, and then finally, you must select a conductor. As a designer, you must account for all of the conditions that the conductors will be exposed to, the temperature that they will operate in, the number of conductors in conduit, the length of the conduit, and the terminals the conductors are attached to each play a role. Proper selection requires following the sequential and methodological process when sizing your conductors. Although this process is common for sizing all conductors, here I specifically address conductor sizing as it pertains to satisfying the National Electrical Code for the DC source and output circuits of PV systems. Throughout this article, the NEC references are from the 2011 version unless otherwise noted. For those familiar with the code, the relocation of tables in Article 310 is the most notable change from earlier versions. Sean here. So I know that this article is from 2011, but hey, sometimes people read books that are 2,000 years old. So 10 years old, that's not that big of a deal. And where there's a few differences in this article between the 2011 version and today's version, what I'm going to do is point out those differences. Also, what it just said here too, is that they are talking about PV source and PV output circuits, but all of this applies to other circuits too, not even just PV, but energy storage and the rest of the National Electrical Code. However, the very confusing part about wire sizing for PV people has to do with how you define current for a solar module. But if you are using electronics, such as DC to DC converters, microinverters, things like that, you really don't need to do anything different than just any regular circuit. Back to the article. Maximum current calculations. The first step, determining the correct current value, is probably the most unique item to PV DC conductors. For most conventional electrical calculations, this is typically simple or at least well understood. PV modules have multiple ratings, are composed of organic materials, silicon's not organic, and they operate with a fluctuating power source. These factors seem to confuse people and may make calculations for PV seem more complicated. Determining the correct value is actually relatively simple once you break it down. Section 690.8 in the 2008 and 2011 NEC outlines the requirements for proper conductor sizing. Shown here again, and that would also pertain through all the NECs, even the 2020 NEC. So look to 690.8 for defining your currents. Section 690.8 defines how to calculate the maximum circuit current. In 2008, an FPN, by the way, FPN stands for fine print note, and now they call that an informational note, which means it's good advice. It's sort of like a yellow traffic sign, and it's not something that you have to follow, but it gives you direction. So in 2008, an FPN was added that states, where 690.8 A1 and B1 are both applied, the resulting multiplication factor is 156%. Historically, many PV designers have used the 1.56 rule to size all DC conductors in all conditions. However, you must understand what the individual components of the 1.56 rule are, so you know when both 690.8 A1 and B1 apply and when they do not. So now I'm looking at the 2020 National Electrical Code, and we still have 690.8 A1, and that's defining our currents. That's 125% of short circuit current for a PV source circuit. And then we have 690.8 B1, and there we are multiplying our maximum currents that we calculated in 690.A by 125%. However, in the 2020 National Electrical Code, they took out that little informational note, or fine print note, or whatever you want to call it, but we still do what that informational note said. It's just that that note confused a lot of people. I thought it was in the wrong place, so they got rid of it. Plus, PV's been around for quite a while, and a lot of us know how to define PV currents. And we're talking wild PV there. That's PV that is a silicon crystal in the sun that turns light into electricity. And since we can't have a dimmer switch for the sun, we're a little bit extra conservative, and we have this 125% of short circuit rule that we use for these PV source circuits. And remember, it's not all DC PV circuits, because you can have DC to DC converter source circuits that's coming out of optimizers where the current is tamed, so it's not wild PV, and we don't have this extra 125% correction factor like we do for PV source circuits. A lot of you are doing PV on buildings, so you don't have to worry about that extra 125%. That extra 125% of a short circuit current. Sections 690.8 A1 and 2 in the NEC define the maximum currents for PV circuits. IMAX, and by the way, IMAX is not an NEC term, that's what they are calling it for this article. IMAX, that means maximum circuit current, is calculated as the sum of parallel module rated short circuit currents multiplied by 125%. So remember, this is just for PV source circuits. The multiplier is needed because solar irradiance fluctuates throughout the day and from region to region. Modules ISC, that's short circuit current ratings, are calculated in laboratory controlled standard test conditions. That's STC of 1000 watts per square meter. Natural conditions are different from STC and give rise to a different current than rated value. Multiplying ISC, that short circuit current, times 1.25 defines what current to use for PV circuits. This is the maximum current expected from PV source and output circuits under extreme conditions of short circuit and high irradiance. Shown here again, hopefully you never short circuit your PV array. This is very conservative. It was put together at a time when PV was so expensive, people would use way bigger wires just to avoid voltage drop losses. Also to note, in the 2020 NEC, we have a new thing here that is 690.8 A1 A2. And this just pretty much tells us that if we have a PV system that's over 100 kilowatts, that's 100 kilowatts AC output, and the calculation has been done by a professional electrical engineer, you can use perhaps as low as 70% of the calculation that we did previously and A1A1. Also, I'd like to point out here too, is they just rearranged the numbering a little bit. So instead of just calling it 690.8A1, it's A1A1. Back to some reading. Overcurrent protection and terminal ratings. Remember, a terminal, that's what you screw your wire into. Now that you have determined Imax per 690.8A1 and 2, you need to determine how to size the conductors based on the terminals used in the junction boxes and overcurrent protection devices, that's OCPDs, where required. 690.8b states that the PV circuits shall be considered to be a continuous load, and that this requires a second 1.25 multiplier. The NEC rules that apply to other continuous loads also apply to PV circuits. The language in 690.8b changed in 2011, clarifying the process and the requirements. The changes do not affect the methodology you need to use when evaluating PV circuits. Sean here again, and one of the things I just want to say is 690.8a defines current, or maximum circuit current, and in this article they're calling it Imax. 690.8b determines conductor ampacity, so that's how much current a conductor can carry under different conditions. Back to reading again. Section 690.8b1a of the 2011 NEC states that overcurrent protection devices shall be sized to carry not less than 125% of the maximum current as calculated in 690.8a. To determine the minimum overcurrent protection device size, multiply the Imax for a given conductor run by 1.25. The resulting continuous current, I-cont, or I-continuous, as they're calling it in this article, I-C-O-N-T, and I just want to say one more thing here, this is Sean again, is that this continuous current is not really a current at all. It is a required ampacity for continuous current. So we're not going to have currents that are this high, but just when you run something for 3 hours or more, you need to oversize your conductors by 25%, and that's common throughout the whole NEC. So back to reading this article. The resulting continuous current, I-cont, is the minimum overcurrent protection device required to protect the conductor in the circuit and the minimum rating of all terminals used to make the wiring connections. Terminal requirements. NEC section 690.8b1b requires you to evaluate the terminal temperature limits independent of the conductor ratings. It is common to use conductors that are rated at 90 degrees C, yet the terminals they are connected to are rated for only 75 degrees C. That's right, usually your conductors are rated at 90 degrees C and your terminals are rated at 75 degrees C. This requires that you evaluate the conductor ampacity values twice, once at the terminals where the conductor is considered 75 degrees, and again for the length of the run where the conductor's 90 degrees C properties are valid. NEC section 310.15b16, and by the way, in the 2020 NEC, we've gone back to calling this table 310.16, which is perhaps the most popular page in the National Electrical Code. And so we're talking about here too is a table 310.16. So table 310.16 has multiple columns of allowable ampacity arranged according to the conductor's insulation temperature rating. Note the new code reference, remember this was written in 2011, for the ampacity table, previously table 310.16. So that means in the 2008 National Electrical Code, it was 310.16. So for the 2011, 2014, and 2017 NEC, they called it 310.15b16. And now, back in the 2020 National Electrical Code, it's back to being called Table 310.16. So, to find the minimum conductor size, look at the thermal ratings of the devices that the conductor is terminated on. Regardless of the insulation of your selected conductor, the conductor shall have a greater ampacity than the terminal rating. So Sean here again, and then why do we want to look at the terminals this way? And the reason is because the conductor acts like a heat sink to keep the terminal cool. So where you make a connection, there's usually a little bit of extra heat. A little bit of resistance there creates a little bit of extra heat. So if you have a nice big wire there on that terminal, it will take more heat away from that terminal. It's called a heat sink. Anyway, back to the article again. Use the column that corresponds with the thermal rating of the terminals. For terminals used in conjunction with PV circuits, the most common rating is 75 degrees C. To satisfy 690.8b1b, select a conductor that has an ampacity rating in the proper terminal thermal rating column that is greater than the calculated I cont, I continuous, or overcurrent protection device required. For example, consider a PV output circuit. And so once again, a PV output circuit is coming out of a combiner after you parallel together PV source circuits. So for example, consider a PV output circuit that has a rating of 50 amps and is connected to a terminal that is rated at 75 degrees C. And so here it says I max equals 1.25 times 50 amps equals 62.5 amps. And then over here, we have I continuous equals 1.25 times 62.5 amps equals 78.1 amps. So pretty much what we're doing here is we are just multiplying our 50 amps times 1.25 and multiplying it by 1.25 again, which 1.25 times 1.25 is 1.56. Some people think that's a magic number. And that is giving us 50 amps times 1.56 equals 78.1 amps. And that was for a 50 amp PV output circuit. That would be a PV output circuit with a short circuit current of 50 amps. As far as I know, there's never been a PV source circuit with any current as high as 50 amps. That would be way up there. According to table 310.15b16 or 310.16, depending on which version of the code you're reading, under the 75C column, 4AWG is the smallest conductor that has an ampacity greater than 78.1 amps. So now what I'm going to do is I'm going to look at the National Electrical Code. That would be the 2020 version of it. And I'm going to look down the 75C column and see which conductor has at least 78.1 amps in the 75C column. And I can see that a 6 AWG wire is 65 amps, so that doesn't quite cut it. But a 4 AWG wire is 85 amps. And if we're looking at these tables in the 2020 National Electrical Code or any version of the National Electrical Code, they pretty much don't change. They're kind of based on physics. OCPD requirements. Section 690.8b1c in the 2011 National Electrical Code requires that OCPD ratings are corrected per the manufacturer's instructions when the system is operating at temperatures greater than 40 degrees C. This is a site and material specific consideration, given that fuses are the most typical type of OCPD used in these locations and that fuse ampacities change along with conductor ampacities. This will generally not be an issue, as long as a fuse properly protects the conductor in normal operating temperatures. It will continue to protect the conductor in elevated temperatures. However, in extreme elevated temperatures, the fuse could nuisance trip if not corrected for temperature. So this is the type of a thing that you might worry about if you're putting together a $1 billion solar farm. And you know what? I've had people that put together $1 billion solar farms in my classes. So when you're spending $1 billion, you really want to make sure that you get everything just right, and you might call the manufacturer. OCPD ratings are defined in section 240.4b, c, and d, where the OCPD is rated at 800 amps or less. 240.4b allows you to use the next higher standard overcurrent protection device above the ampacity of the conductors being protected. Now, this is the real confusing thing about wire sizing. Once again, let's read this again. 240.4b allows you to use the next higher standard overcurrent protection device above the ampacity of the conductors being protected. That means that in some cases, you can use an overcurrent protection device that is rated for a current that is higher than the ampacity of the conductor being protected. That is not very intuitive. We're going to get into that more and more, but that is kind of crazy what a lot of people would think. The reason why we can do this, because that table that we were looking at, table 310.16, is very conservative. So those conductors, whatever they're rated for, they can take more current than what they're rated for. But remember, this doesn't happen every time. It's just a once in a while thing where you could have a situation where the ampacity of your wire is less than the current rating of your overcurrent protection device. But there's no rule that says that you cannot make your wire bigger. So you're encouraged to make your wire bigger. This would be hard to explain to an inspector that says, why is the ampacity of your wire less than your overcurrent protection device? We don't allow that in this town. Be careful about applying this allowance to size the conductor below the overcurrent protection device rating, especially when dealing with small currents and sizing conductors from modules to a string combining device. This is because Section 690.9c photovoltaic source circuit states that standard overcurrent protection device values used for source circuits shall be in 1 ampere size increments starting at 1 amp up to and including 15 amps. So remember, this article was based on the 2011 National Electrical Code, and they changed that in the 2014 National Electrical Code. So now, instead of 1 amp increments below 15 amps, we have 1 amp, 3 amp, 6 amps, and 10 amps. And then you go to 15 amps, which is also a standard size. So pretty much we'll be dealing with 15 amps. We're not going to be dealing with 14 amp fuses. And if you wanted to see your standard sizes for fuses, you can go to 240.6a. So like I said, there's a couple of things in this article, and one of them has to do with these 1 amp increments were taken out of the code in the 2011 National Electrical Code after the 2011 National Electrical Code. And the other thing that's different about this article is they got rid of the temperature adder for conduit and sunlight on a rooftop. So you don't have to worry about that one either, and that one's coming up. This ability to use the next standard size requires that you evaluate the conductors used in the source circuits and verify that they have the correct ampacity for their conditions of use. In addition, be sure not to exceed the module's maximum series fuse rating. Now, if you're getting confused a little bit, I have a 10-step process that I go over in my books, PV and the NEC, and PV Engineering and Installation. Plus, of course, I'm going to go in detail in my advanced heat spring classes. Sizing the conductors. The final step necessary to meet Section 690.8 requirements is to select a conductor that can handle the current and will be protected by the overcurrent protection device under 690.8 B2. The 2011 NEC offers 2 different methodologies to properly select a conductor. You need to do both calculations and then choose the larger conductor. Under 690.8 B2A, the first test is to find the conductor ampacity that is greater than 156% of ISC. So if you're not sizing a PV source circuit, it would be greater than 125% of maximum circuit current. There are no conditions of use applied here, only the 2 125% factors. The second test under 690.8 B2B is to apply conditions of use to the Imax found in 690.8A. It is worth noting that the second method uses the value for Imax found after multiplying ISC times 1.25 only once. So yes, there's a couple of different paths that we go by. One pathway is you take maximum circuit current times 1.25, and you would perhaps do that in the 75-degree terminal column. And the other pathway is you just take maximum circuit current and you don't use a 1.25, and you might be checking that out in the 90C column after applying conditions of use. So what are conditions of use? Those are things that heat up your wire, those conditions. And remember, I told you we got rid of one of those conditions, and that's for conduit over rooftop in sunlight. However, I'm still going to read that anyway, because I am reading every word here in this article as I help explain things. Adding conditions of use. Conditions of use are defined by the temperature the conductors are exposed to at the site and the number of conductors that are run in close proximity to each other according to the correction factor subsections of Section 310.15, Table 310.15b3a, which provides adjustment factors for conductors running in conduit or bundled together. Now, one thing that I'm going to tell you here too is they changed the name of Table 310.15b3a. And now the name of Table 310.15b3a in the 2020 National Electrical Code, when it was changed, it is called Table 310.15c1 adjustment factor for more than 3 current carrying conductors. So if you feel like pausing and memorizing things, it's kind of a simple table, and we have 4 to 6 conductors. That's 80% derating, so it can only take 80% of the current if we have too many conductors in that conduit. 7 to 9 is 70%, 10 to 20 is 50%, 21 to 30, 45%, 31 to 40, 40%, and 41 and above conductors in conduit can only take 35% of the current. This table hasn't changed except for the name. It's changed to 310.15 C1. Maybe think of that C1 as your top vertebrae in your neck called your atlas, and you've got all your cranial nerves going through there, through the C1, and they're all bundled together. So they're going to heat up as you're sending all those nervous impulses back and forth. That's table 310.15 C1 instead of table 310.15 B3A, which provides adjustment factors for conductors run in a conduit or bundled together in continuous lengths greater than 24 inches. So if you're going less than 2 feet, you don't have to use table 310.15 C1. Only if you're going greater than 24 inches. Table 310.15 B3C provides temperature adjustment factors for circular raceways along rooftops. And that was the table that we do not have to use anymore. So do not use table 310.15 B3C. Those are the temperature adjustment factors for circular raceways above the rooftops. That was removed in the 2017 National Electrical Code. However, there are a few places in the United States still using the 2014 NEC and the 2011 NEC and the 2008 NEC, so there might be somebody out there that still has to do that. To determine the conditions of use, first determine your ambient temperature. This sounds simple, but it has caused many a debate in many jurisdictions. The 2008 National Electrical Code added a note, that's an FPN, at the end of section 310.15 B2 that states, one source for the average ambient temperatures in various locations is the ASHRAE, that's American Society for Heating, Refrigeration, Air Conditioning Engineers Handbook, and so this indicates that an average high should be used. The Solar ABC's website, and I'm always going there for these temperatures, and that's solarabcs.org. If you want, you could go /permitting to get you there quicker. Provides a readily accessible source for the ASHRAE data. You can search for this location based on zip code, and the site returns ASHRAE data from local weather stations. The data include 2 high temperature values, the 0.4% temperature value and the 2% average values in degrees C. Most people in the solar industry use the 2% high design ASHRAE tables as the standard for design temperatures. So that means during the 3 hottest months of the year, that 2% of the time it will get hotter than this temperature. So we're using more of an average value. And the 0.4% is more conservative. So you don't have to use the 0.4 unless somebody makes you. The 2% average ASHRAE temperature is the one that you want to look for. You should determine if the jurisdiction you are designing for has published engineering standards that include design temperatures. The same design temperatures used for other engineering disciplines should be consistently applied to PV applications. If the jurisdiction does not have published design temperature information, ASHRAE tables are the safest and most accurate source for the information. Once you have determined your starting design temperature, you have to determine the other conditions of use. Is your conductor in free air or is it in conduit? So free air, that's table 310.17. Conduit is table 310.16. Is it exposed to sunlight? We don't have to worry about that anymore. How far from the roof is it installed? We don't have to worry about that anymore because they got rid of table 310.15 B3C. How many current carrying conductors are there in the same conduit? What's that table? That's 310.15 C1. Conductors are often exposed to many different conditions of use in a single run. Technically, you should do calculations for each unique condition. However, the most important thing to do is the calculation for the worst case. The worst case is the maximum correction factor caused by the coincident conditions that result in the lowest ampacity of the conductor. So one of the things that you do with wire sizing is you do different checks. You don't stack all of your calculations on top of each other always. You do this check for this and that check for that, and then you end up using the biggest wire. Exceptions can often come into play. Section 310.15b3a2 states, adjustment factors shall not apply to conductors in raceways having a length not exceeding 24 inches. The exception to Section 310.15a2 states, where two or more different ampacities apply to adjacent portions of a circuit, the higher ampacity shall be permitted to be used beyond the point of transition, a distance equal to 10 feet or 10% of the circuit length figured at the higher ampacity, whichever is less. So let's say that you had a 100-foot wire run and 10 feet of that was going outside. Well, that's 10%, and it also happens to be 10 feet. So you don't have to worry about that 10 feet that's going outside because it's 10 feet or 10% or whatever is less. And of course, this also goes for the 2020 National Electrical Code. So that's sort of like a little exception you have there. Worst case conditions. The following example illustrates the method for determining the worst case condition for the conductor. Consider the PV source circuit conductors from a module to a string combiner. A conductor leaves the module in free air secured 3.5 to 12 inches off a roof. It passes through a 12-inch conductor tray located 0 to 0.5 inches off a roof. By the way, those are things that we don't have to consider anymore. That's conduit on sunlight on a rooftop. So we're considering this conductor, and also that conductor is with 4 other conductors. Okay, that's greater than 3 current carrying conductors in a raceway. I'm thinking 310.15c1. And then it is bundled with 19 other conductors, that's a lot, in free air supported at 0.5 to 3.5 inches off the roof. So remember, off the roof part we don't have to worry about. Finally, for physical protection, it passes through 36 inches of EMT, that's greater than 24 inches, conduit that is secured at 3.5 to 12 inches off the rooftop before entering a combiner box. You do not need to consider each individual worst-case condition, but you should consider the coincident worst-case conditions. When the conductor passes through the conductor tray, remember that was 12 inches long, at 0 to 0.5 inches off the roof, which we don't have to worry about, Section 310.15b3a2 applies because the conduit, that's the conductor tray, not the EMT that we were talking about, was less than 24 inches long. It was 12 inches long. It's the EMT that's 36 inches. The bundled conductors are subject to Section 310.15b3a. Because the conductors are in free air, you do not need to apply the 0.5 to 3.5 inches sunlight exposed temperature increase for conductor, and you don't have to apply that for conduit anymore, nor consider the conductor in a conduit. The worst case in this example is a 20 conductor conduit fill and 3.5 to 12 inches sunlight exposed temperature increase. So we're just talking about the conduit fill of 20 conductors, and we don't have to worry about the 3.5 to 12 inches sunlight exposed. Use the ampacity tables from Table 310.15b16, which is now known as Table 310.16, for conductors installed in conduit. Final considerations. Once you have defined the conditions of use, refer to the NEC tables for adjustment values. You now have to consider the conductor's insulation rating instead of looking at the thermal rating of the terminal device. It's a different step. You must consider the thermal rating of the conductor in tables 310.15b16, that's table 310.16, when conductors are in raceways, and table 310.15b17, which is now table 310.17, when they are in free air. One way I like to remember this is table 310.17 is for free air, and table 310.16 is for everything else, including being buried, because being buried is not free air. You use both the ampacity value and the thermal correction factor from the column that corresponds with the chosen conductor type. The thermal correction factors were relocated to Section 310.15b2a in the 2011 National Electrical Code. For most PV/DC applications exposed to extreme conditions of use, it is best to select a 90C rated conductor. Currently, most installers use USE2 for free air and THWN-2 in conduit. And I would like to add, besides using USE2 for free air, PV wire is very popular too. To choose a properly sized conductor, compare the conditions of use corrected conductor ampacity to the IMAX current and chosen overcurrent protection device. You do not compare the corrected conductor to the continuous current. That means required ampacity for continuous current, and that's short circuit current times 1.56, but rather only I max. I call that rated current, and that is short circuit current times 1.25 for a PV source circuit. And by the way, for most things, I max is just the current that it is. You don't have an extra 1.25, just for special PV source circuits. This is an important distinction. You also need to verify that the conductor's ampacity without conditions of use adjustments exceeds the continuous current value to avoid conductors that are larger than necessary. The sample calculations on pages 18 and 20 walk through this project step by step. And so besides reading these calculations, that's the end of the article, and it was written by Jason Sharp of Namaste Solar in Denver, Colorado. Namaste. So hey, you podcast people out there, it's a little bit difficult to just read a calculation. In fact, it might have been difficult to even understand some of the things that I was reading from this article. But put it under your pillow, listen to it for 365 nights in a row, and I guarantee you will know this material. You might also be kind of sick of my voice by then. Or, if I ever meet you and I say something, you will immediately fall asleep. And if you want to look at these examples, just go to solarprofessional.com and read wire sizing article from April-May 2011. Or check it out in my heat spring classes. Thanks for listening to Sean White's Solar and Energy Storage Podcast. I hope you understand that wire sizing can be difficult and perhaps have learned something here. To learn more about solar and energy storage, go to solarsean.com. That's solar, SEAN.com.